Distributions are objects that generalize the classical notion of functions in mathematical analysis. Distributions make it possible to differentiate functions whose derivatives do not exist in the classical sense. In particular, any locally integrable function has a distributional derivative. Distributions are widely used in the theory of partial differential equations, where it may be easier to establish the existence of distributional solutions than classical solutions, or appropriate classical solutions may not exist. Distributions are also important in physics and engineering, where many problems naturally lead to differential equations whose solutions or initial conditions are distributions, such as the Dirac delta function. The practical use of distributions can be traced back to the use of green functions in the 1830s to solve ordinary differential equations, but was not formalized until much later. According to Kolmogorov and Fomin, generalized functions originated in the work of Sergei Sobolev on second-order hyperbolic partial differential equations, and the ideas were developed in somewhat extended form by Laurent Schwartz in the late 1940s. According to his autobiography, Schwartz introduced the term distribution by analogy with a distribution of electrical charge, possibly including not only point charges but also dipoles and so on. Garding comments that although the ideas in the transformative book by Schwartz were not entirely new, it was Schwartz's broad attack and conviction that distributions would be useful almost everywhere in analysis that made the difference. The basic idea in distribution theory is to reinterpret functions as linear functionals acting on a space of test functions. Standard functions act by integration against a test function, but many other linear functionals do not arise in this way, and these are the generalized functions. There are different possible choices for the space of test functions, leading to different spaces of distributions. The basic space of test function consists of smooth functions with compact support, leading to standard distributions. Use of the space of smooth, rapidly decreasing test functions gives instead the tempered distributions, which are important because they have a well-defined distributional Fourier transform. Every tempered distribution is a distribution in the normal sense, but the converse is not true. In general, the larger the space of test functions, the more restrictive the notion of distribution. On the other hand, the use of spaces of analytic test functions leads to Sato's theory of hyperfunctions. This theory has a different character from the previous ones, because there are no analytic functions with non-empty compact support. Basic idea: distributions are a class of linear functionals that map a set of test functions into the set of real numbers. In the simplest case, the set of test functions considered is D, which is the set of functions phi r having two properties. Phi is smooth. Phi has compact support. A distribution T is a linear mapping T. dr. Instead of writing T, it is conventional to write for the value of T acting on a test function phi. A simple example of a distribution is the Dirac delta delta, defined by meaning that delta evaluates a test function at 0. Its physical interpretation is as the density of a point source. As described next, there are straightforward mappings from both locally integrable functions and radon measures to corresponding distributions, but not all distributions can be formed in this manner. Functions and measures as distributions suppose that f r is a locally integrable function. Then a corresponding distribution Tf may be defined by this integral as a real number which depends linearly and continuously on phi. Conversely, the values of the distribution Tf on test functions indeed determine the pointwise almost everywhere values of the function f on R. In a conventional abusive notation, f is often used to represent both the original function f and the corresponding distribution Tf. This example suggests the definition of a distribution as a linear and, in an appropriate sense, continuous functional on the space of test functions D. Similarly, if mu is a radon measure on R, then a corresponding distribution R mu may be defined by this integral also depends linearly and continuously on phi, so that R mu is a distribution. If mu is absolutely continuous with respect to Lebesgue measure with density f and d mu equals f dx, then this definition for R mu is the same as the previous one for Tf, but if mu is not absolutely continuous, then R mu is a distribution that is not associated with a function. For example, if P is the point mass measure on R that assigns measure 1 to the singleton set 0, and measure 0 to sets that do not contain 0, then so that Rp equals delta is the Dirac delta. Adding and multiplying distributions. Distributions may be multiplied by real numbers and added together, so they form a real vector space. Distributions may also be multiplied by infinitely differentiable functions. But it is not possible to define a product of general distributions that extends the usual pointwise product of functions and has the same algebraic properties. Derivatives of distributions. It is desirable to choose a definition for the derivative of a distribution which, at least for distributions derived from smooth functions, has the property that, if phi is a test function, we can use integration by parts to see that where the last equality follows from the fact that phi has compact support, so is 0 outside of a bounded set. This suggests that if T is a distribution, we should define its derivative T by it. Turns out that this is the proper definition. It extends the ordinary definition of derivative. Every distribution becomes infinitely differentiable, and the usual properties of derivatives hold. Example: recall that the Dirac delta is the distribution defined by the equation. It is the derivative of the distribution corresponding to the Heaviside step function h for any test function phi, so h equals delta. Note, phi equals 0 because phi has compact support by our definition of a test function. Similarly, the derivative of the Dirac delta is the distribution defined by the equation. This latter distribution is an example of a distribution that is not derived from a function or a measure. Its physical interpretation is as the density of a dipole source. Test functions and distributions. In the following, real-valued distributions on an open subset U of Rn will be formally defined. With minor modifications, one can also define complex-valued distributions, and one can replace Rn by any smooth manifold. The first object to define is the space D of test functions on U. Once this is defined, it is then necessary to equip it with a topology by defining the limit of a sequence of elements of D. The space of distributions will then be given as the space of continuous linear functionals on D. Test function space. The space D of test functions on U is defined as follows. A function phi UR is said to have compact support if there exists a compact subset K of U such that phi equals 0 for all x in U, K. The elements of D are the infinitely differentiable functions phi UR with compact support, also known as bump functions. This is a real vector space. It can be given a topology by defining the limit of a sequence of elements of D. A sequence in D is said to converge to phi D if the following two conditions hold. There is a compact set Ku containing the supports of all phi k. For each multi-index alpha, the sequence of partial derivatives tends uniformly to. With this definition, D becomes a complete locally convex topological vector space satisfying the Heine-Borel property. This topology can be placed in the context of the following general construction. Let be a countable increasing union of locally convex topological vector spaces and iota I. Xi X be the inclusion maps. In this context, the inductive limit topology, or final topology, tau on X is the finest locally convex vector space topology making all the inclusion maps continuous. The topology tau can be explicitly described as follows. Let B to be the collection of convex balanced subsets W of X such that W she is open for all I. A base for the inductive limit topology tau then consists of the sets of the form X plus W, where X in X and W in beta. The proof that tau is a vector space topology makes use of the assumption that each she is locally convex. By construction, beta is a local base for tau. That any locally convex vector space topology on X must necessarily contain tau means it is the weakest one. One can also show that, for each I, the subspace topology she inherits from tau coincides with its original topology. When each she is a fresh A space, is called an LF space. Now let U be the union of UI where UI is a countable nested family of open subsets of U with compact closures key equals UI. Then we have the countable increasing union where decay I is the set of all smooth functions on U with support lying in key. On each decay I, consider the topology given by the seminorms, i.e., the topology of uniform convergence of derivatives of arbitrary order. This makes each decay I a fresh A space. The resulting LF space structure on D is the topology described in the beginning of the section. On D, one can also consider the topology given by the seminorms. However, this topology has the disadvantage of not being complete. On the other hand, because of the particular features of DKIs, a set this bounded with respect to tau if and only if it lies in some DKIs. The completeness of tau then follow from that of DKIs. The topology tau is not metrizable by the back-category theorem, since D is the union of subspaces of the first category and D. Distributions. A distribution on U is a continuous linear functional T, DRC. That is, a distribution T assigns to each test function phi a real scalar T such that for all test functions phi1, phi2 and scalars C1, C2. Moreover, T is continuous if and only if for every convergent sequence phi k in D is not metrizable. A linear functional on D is continuous if and only if it is sequentially continuous. Equivalently, T is continuous if and only if for every compact subset K of U there exists a positive constant Ck and a non-negative integer Nk such that for all test functions phi with support contained in K in all multi-indices alpha with alpha Nk. The space of distributions on U is denoted by D, and it is the continuous dual space of D. No matter what dual topology is placed on D, a sequence of distributions converges in this topology if and only if it converges pointwise, which is why the topology is sometimes defined to be the weak asterisk topology, but often the topology of bounded convergence, which in this case is the same as the topology of uniform convergence on compact sets, is placed on D, since it is with this topology that D becomes a nuclear Montel space, and it is with this topology that the kernel's theorem of Schwarz holds. No matter which topology is chosen, D will be a non-metrizable, locally convex topological vector space. The duality pairing between a distribution T in D, and a test function phi in D is denoted using angle brackets by so that T, phi equals T. One interprets this notation as the distribution T acting on the test function phi to give a scalar, or symmetrically as the test function phi acting on the distribution T. A sequence of distributions converges with respect to the weak asterisk topology on D, to a distribution T if and only if for every test function phi in D. For example, if fk r is the function and tk is the distribution corresponding to fk, then as k infinity, so tk delta in D. Thus, for large K, the function fk can be regarded as an approximation of the Dirac delta distribution. Functions as distributions. The function f UR is called locally integrable if it is Lebesgue integrable over every compact subset K of U. This is a large class of functions which includes all continuous functions and all LP functions. The topology on D is defined in such a fashion that any locally integrable function f yields a continuous linear functional on D, that is, an element of D, denoted here by Tf, whose value on the test function phi is given by the Lebesgue integral. Conventionally, one abuses notation by identifying Tf with f, provided no confusion can arise. And thus the pairing between Tf and phi is often written if f and g are two locally integrable functions. Then the associated distributions Tf and Tg are equal to the same element of D, if and only if f and g are equal almost everywhere. In a similar manner, every radon measure mu on U defines an element of D, whose value on the test function phi is phi d mu. As above, it is conventional to abuse notation and write the pairing between a radon measure mu and a test function phi as. Conversely, as shown in a theorem by Schwarz, every distribution which is non-negative on non-negative functions is of this form for some radon measure. The test functions are themselves locally integrable, and so define distributions. As such, they are dense in D, with respect to the topology on D, in the sense that for any distribution Td, there is a sequence phi nd such that for all psi d. This fact follows from the Hahn-Banach theorem, since the dual of D, with its weak asterisk topology is the space D, and it can also be proven more constructively by a convolution argument. Operations on distributions. Many operations, which are defined on smooth functions with compact support, can also be defined for distributions. In general, if A, dd is a linear mapping of vector spaces which is continuous with respect to the weak asterisk topology, then it is possible to extend A to a mapping A, d by passing to the limit. In practice, however, it is more convenient to define operations on distributions by means of the transpose. If A, dd is a continuous linear operator, then the transpose is an operator at dd such that if such an operator it exists and is continuous on D, then the original operator A may be extended to D, by defining it for a distribution T as differentiation. Suppose A, dd is the partial derivative operator if phi and psi are in D, then an integration by parts gives so that it equals minus A. This operator is a continuous linear transformation on D. So, if Td is a distribution, then the partial derivative of T with respect to the coordinate xk is defined by the formula with this definition. Every distribution is infinitely differentiable, and the derivative in the direction xk is a linear operator on D. More generally, if alpha equals is an arbitrary multi-index and alpha is the associated partial derivative operator, then the partial derivative alpha t of the distribution Td is defined by differentiation of distributions as a continuous operator on D. This is an important and desirable property that is not shared by most other notions of differentiation. Multiplication by a smooth function if m UR is an infinitely differentiable function and T is a distribution on U. Then the product mount is defined by this definition coincides with the transpose definition since if m dd is the operator of multiplication by the function m, then so that mount equals m. Under multiplication by smooth functions, D is a module over the ring C infinity. With this definition of multiplication by a smooth function, the ordinary product rule of calculus remains valid. However, a number of unusual identities also arise. For example, if delta is the Dirac delta distribution on R, then m delta equals m delta, and if delta is the derivative of the delta distribution, then these definitions of differentiation and multiplication also make it possible to define the operation of a linear differential operator with smooth coefficients on a distribution. A linear differential operator P takes a distribution Td to another distribution Pt given by a sum of the form where the coefficients P alpha are smooth functions on U. The action of the distribution pt on a test function phi is given by the minimum integer k for which such an expansion holds for every distribution T, is called the order of P. The space D is a D-module with respect to the action of the ring of linear differential operators. Composition with a smooth function. Let T be a distribution on an open set URn. Let V be an open set in Rn, and F VU. Then, provided F is a submersion, it is possible to define this as the composition of the distribution T with F, and is also called the pullback of T along F. Sometimes written, the pullback is often denoted F asterisk, although this notation should not be confused with the use of asterisk to denote the adjoint of a linear mapping. The condition that F be a submersion is equivalent to the requirement that the Jacobian derivative df of F is a surjective linear map for every xv. A necessary condition for extending f' to distributions is that F be an open mapping. The inverse function theorem ensures that a submersion satisfies this condition. If F is a submersion, then f' is defined on distributions by finding the transpose map. Uniqueness of this extension is guaranteed since f' is a continuous linear operator on D. Existence, however, requires using the change of variables formula, the inverse function theorem, and a partition of unity argument. See Hallmander. In the special case when F is a diffeomorphism from an open subset V of Rn onto an open subset U of Rn, change of variables under the integral gives. In this particular case, then, f' is defined by the transpose formula.